Let's start by understanding what Helm is. Now, Kubernetes is awesome at managing complex infrastructures. We humans tend to struggle with complexity, though. Applications that we deploy into our Kubernetes cluster can become very complicated. A typical app is usually made up of a collection of objects that need to interconnect to make everything work. For example, even a relatively simple WordPress site might need the following: a deployment to deploy the pods that you want to run, such as MySQL database servers or web servers, a persistent volume to store the database, a persistent volume claim, a service to expose the web server running in a pod to the internet, a secret to store credentials like admin passwords and other things, and maybe even more if you want extra stuff like periodic backups, jobs, and so on. For every object, we might need a separate YAML file. Then we need to apply kubectl apply on every YAML file to get these objects created. And this can be a tedious task, but that's not the end of it. Now imagine we download these YAML files from the internet and we're not happy with the defaults, so we start changing stuff. The persistent volumes are 20 GB, but we know our website will need much more storage than that. So we go to the YAML files where the PVs and PVCs are declared and we change 20 to 100. More stuff needs to be changed. We'll have to open up every YAML file and edit each one according to our needs. And now, not bad enough yet. Now imagine 2 months go by and we now have to upgrade some components in our app. And so we're back to editing multiple YAML files declarations again with great care so that we don't change the wrong thing in the wrong place. Now, sometime later, you want to delete the app, and we'll need to remember each object that belongs to our app and delete them all one by one. Now, you might be thinking, hey, that's not a big deal. We can just write all object declarations in a single YAML file and be done with it. Well, that's true, but it might make it even harder to find stuff when you're looking for, say, you want to troubleshoot an issue. We'd have to continuously search for stuff that we need to edit in something that could be 25 pages of text. And at least in multiple files, they'd be somewhat organized, and we'd know we'll find deployment-related stuff in the mydeployment.yaml file, for example. Enter Helm. Helm changes the paradigm. Kubernetes doesn't really care about our app as a whole. All that it knows is that we declared various objects, and it proceeds to make each of them exist in our cluster. It doesn't really know that this persistent volume and that deployment and that secret and that service are all part of a big application called WordPress. It looks at all the little pieces that the administrator wanted to have in the cluster and takes care of each one individually. Helm, however, is built from ground up to know about such stuff. That's why it's sometimes called a package manager for Kubernetes. It looks at those objects as part of a big package as a group. And whenever we need to perform an action, we don't tell Helm the objects that it should touch. We just tell it what package we want to act on, like our WordPress app package. And based on the package name, it then knows what objects it should change and how, even if there are hundreds of objects that belong to that particular package. Now, to make this easier to understand, think about this. A computer game is contained in hundreds of thousands of files. There are a few files with the program's executable code, other files with audio, game sounds, and music, and other files with graphics, textures, images, files with configuration data, and so on. Now imagine we'd have to download each of them separately, and that would be tedious. Fortunately, we don't have to go through such horrors as we get a game installer. We run it, we choose the directory where we want to install, we press the install button, and then the installer does the rest, putting thousands of files in their proper location. Helm does a similar thing and more for the YAML files and the Kubernetes objects that make up our application. We use a single command to install our entire app, even if it needs hundreds of objects. Helm proceeds to automatically add every necessary object to Kubernetes without bothering us with the details. We can customize the settings we want for our app or package by specifying desired values at install time. But instead of having to edit multiple values in the multiple YAML files, we have a single location where we can declare every custom setting. In a file like values.yaml, we can change the size of our persistent volumes, choose the name of our WordPress website, the admin password, settings for the database engine, and so on. We can upgrade our application with a single command. Helm will know what individual objects need to change to make this happen. Helm keeps track of all the changes made to the app files, and that allows us to roll back to the previous so-called revision. We use a single command to uninstall our app, and it keeps track of all the objects used by each app, so it knows what to remove. We don't need to remember each object that belongs to our one of our apps anymore, or use 10 separate commands to remove everything. Helm does all the work. We will look into these commands in more detail in the upcoming lectures. For now, understand that Helm works as a package manager with install or uninstall wizard, and also as a release manager, helping us upgrade or roll back applications. The most important thing is that it lets us treat our Kubernetes apps as apps instead of just a collection of objects. And this takes a huge burden off our shoulders, as we don't have to micromanage each Kubernetes object anymore. Helm can do that for us. Well, that's a quick introduction to Helm. We have a lot more to discuss. I'll see you in the next one. In this section, we will talk briefly about installing Helm. And before installing Helm, you must first have a functional Kubernetes cluster and kubectl installed and configured on your local computer with the right login details set up in the kubeconfig file to work with the intended Kubernetes cluster. Now, Helm can be installed on Linux, Windows, or Mac OS systems. We will go over the instructions on installing Helm on Linux systems in this lecture. Systems with snap can install Helm using the snap install Helm command. Use the classic option to install a more relaxed sandbox that gives the app a bit more access to the host system. So rather than strictly isolating it to its separate environment, this way, Helm can easily access the kubeconfig file in your home directory, so it knows how to connect to our Kubernetes cluster. For APT-based systems, such as Debian or Ubuntu, follow the instructions to add key and sources list before installing Helm. And for PKG, run the package install Helm command. Now, always refer to the latest instructions from the documentation pages to install Helm for your version of operating system. Well, that's all for now. Head over to the labs and practice working with installing Helm on our lab environment. There were some significant changes when Helm 3 was released compared to Helm 2, and when you browse through charts and blogs online, you may come across either of these versions. So it is important to understand the differences between them. Now let's look at a brief history of Helm. Helm 1.0 was first released in February 2016, Helm 2.0 in November 2016, and Helm 3.0 in November 2019. Now, since the initial launch in 2016, the project has matured and it got better and better. The improvements were also made possible by the fact that Kubernetes itself was improving. So Helm had more tools at its disposal it could leverage right off of Kubernetes. In our lessons, we'll use Helm 3, which has a simpler and better design than the previous Helm 2 and is also a bit smarter. Since Helm 2 was around for a few years, a lot of users had already been using it, but there are several important changes made when Helm 3 was launched. So let's take a look at the differences between them. Helm has a CLI client installed on your local machine that helps you perform Helm-specific actions against your Kubernetes cluster. When Helm 2 was around, Kubernetes lacked features such as role-based access control and custom resource definitions. To allow Helm to do its magic, an extra component called Tiller had to be installed in the Kubernetes cluster. So whenever you wanted to perform a Helm-specific operation, your Helm client communicated with Tiller that was running on some server. Tiller, in turn, communicated with Kubernetes and proceeded to take actions to make whatever you requested happen. So Tiller was the middleman, so to speak. Besides the fact that an extra component sitting between you and Kubernetes adds complexity, there were also some security concerns. By default, Tiller was running in God mode, or otherwise said, it had the privileges to do anything that it wanted. This was good since it allowed it to make whatever changes necessary in your Kubernetes cluster to install your charts, but this was bad since it allowed any user with Tiller access to do whatever they wanted in the cluster. After cool stuff like role-based access control and custom resource definitions appeared in Kubernetes, the need for Tiller decreased, and so it was removed entirely in Helm 3. Now there's nothing sitting between Helm and the cluster. Furthermore, with RBAC, security is much improved and any user can be limited in what they can do with Helm. Before you had to set these limits in Tiller, and that was not the best option, but with RBAC built from ground up to fine-tune user permissions in Kubernetes, it's now straightforward to do. As far as Kubernetes is concerned, it doesn't matter if the user is trying to make changes within the cluster with kubectl or with Helm commands. The user requesting the changes has the same RBAC allowed permissions, whatever tool they use. So that's a big difference between Helm 2 and 3. Helm 2 had Tiller, and Helm 3 simplifies integration with Kubernetes by removing Tiller. The next big difference is a 3-way strategic merge patch. The name might sound intimidating, but don't worry. At the end of this section, we'll see it's actually a simple but very smart thing that can prove quite useful. Now, Helm has something like a snapshot feature. Here's an example. You can use a chart to install a full-blown WordPress website. This will create revision number 1 for this install. Then if you change something, for example, you upgrade to a newer chart to upgrade your WordPress install, you will arrive at revision number 2. These revisions can be considered something like snapshots, the exact state of a Kubernetes package at that moment in time. If there's a need, you can return to revision number 1, do a rollback. This would get your package app to the same state it was when you first installed your chart. New revisions are created whenever important changes are done with the Helm command. For example, when we first install a package, a revision 1 is created. Then when we upgrade that package, a new revision appears, that's revision 2 in this case. And even when we roll back, a new revision is created, revision 3. So that's pretty straightforward. Helm 2 was less sophisticated when it came to how it did such rollbacks. And when a rollback command is issued, Helm compares the current chart, which is the chart that has the WordPress image 5.8 in it, with the previous chart, which is the chart that has a WordPress 4.8 image in it, and realizes that they are different. So it applies the original chart to revert the WordPress image to 4.8. Now let's look at another example. Say we install a WordPress deployment using a Helm chart which creates revision 1, just like before. Then a user manually goes in and updates the application image using the kubectl set image command. So the application gets updated, and this is done instead of doing the upgrade through Helm. And this does not create a new revision in Helm because the change was not performed through Helm. When we now roll back, what happens? As before, Helm compares the current revision with the previous version. Since there is only one revision, Helm does not detect any changes, and so it does not roll back or make any changes to the deployment. So Helm 2 compares the current chart with the previous chart to identify the difference between revisions to make a rollback decision. And in this case, it doesn't help us because the manual change that the user made is still active. Helm 3, on the other hand, is more intelligent. It compares the chart currently in use if we had created a revision, that is, which we didn't, the chart we want to revert to, and also the live state, how our Kubernetes objects currently look like, their declarations in the YAML form. This is where that fancy three-way strategic merge patch name comes from. By also looking at the live state, it notices that the image version in live is 5.8, but the image in revision 1 that we want to revert to is at 4.8. So it makes necessary changes to come back to the original state. Now, besides rollbacks, there are also things like upgrades to consider, where helm2 was also lacking. For example, say you install a chart, but then you make some changes to some of the Kubernetes objects installed. It all works nicely until you perform an upgrade. helm2 looks at the old chart and then the new chart that you want to upgrade to, and all your changes will be lost since they don't exist in the old chart or the new chart. But Helm 3, as mentioned, looks at the charts and also at the live state, and it notices that you added some stuff of your own. So it performs the upgrade while preserving anything that you might have added. Well, that's all for this lecture, and I will see you in the next one. Let's look at the different components of Helm. Helm has multiple components we'll be working with. So let's take a look at its general structure, concepts, and the pieces we'll be working with. So we have the Helm command line utility on our local system that we will be using to perform Helm actions, such as installing a chart, upgrading, rollback, etc. Charts are a collection of files, and they contain all the instructions that Helm needs to know to be able to create the collection of objects that you need in your Kubernetes cluster. By using charts and adding the objects according to the specific instructions in the charts, Helm, in a way, installs applications into your cluster. When a chart is applied to your cluster, a release is created. A release is a single installation of an application using a Helm chart. Within each release, you can have multiple revisions, and each revision is like a snapshot of the application. Every time a change is made to the application, such as an upgrade of the image or change of replicas or configuration objects, a new revision is created. Now, just like how we can find all kinds of images on Docker Hub or Vagrant boxes on the Vagrant Cloud, if you're familiar with that, we can find Helm charts in a public repository. We can easily download publicly available charts for various applications, and these are readily available, and we can use them to deploy applications on our cluster. And finally, to keep track of what it did in our cluster, such as the releases that it installed, the charts used, revision states, and so on, Helm will need a place to save this data. This data is known as metadata, and that is data about data. Now, it wouldn't be too useful if Helm would save this on our local computer. If another person would need to work with our releases through Helm, they would need a copy of this data. So instead, Helm does the smart thing and saves this metadata directly in our Kubernetes cluster as Kubernetes secrets. This way, the data survives, and as long as the Kubernetes cluster survives, everyone from our team can access it, so they can do Helm upgrades or whatever it is that they want to do. So Helm will always know about everything it did in this cluster and will be able to keep track of every action, every step of the way, since it always has its metadata available. Now let's look at each of these in a bit more detail. Charts are a collection of files, and they contain all the instructions that Helm needs to be able to create the collection of objects that you need in your Kubernetes cluster. And by using these charts and adding the objects according to the specific instructions is how, as we discussed, Helm installs applications into your cluster. Now, I'll be using two applications throughout this course to explain concepts. First is a simple Hello World application, which is a simple Nginx-based web server and a service to expose it. And the other would be a WordPress site, which is slightly more complex. Now, the simple web server will help you understand the concepts in the simplest form. The WordPress example will help you understand its real-life usage. For example, in this simple Hello World application, we have two objects, a deployment and a service. And most of these you should be able to relate to what you learned in the Kubernetes course. It's a standard deployment object that deploys pods of an image and a service that exposes it as a node port service, for instance. However, you might notice the image name and replicas are specified in a different form. This is called templating. The values that go here are part of another file called as the values.yaml file. Now, in a Helm chart, we'll often be interacting with a special file. You see, most of the time, we won't need to build the charts ourselves. We have hundreds of them already available to download in the public repository, but what we'll almost always need to do or want to do is configure the package that we install through that chart. The values.yaml file is where the configurable values are stored. And most of the time, this is the only file you'll have to modify to customize the deployment of the application for your needs. This is like the settings file or the inputs file for the Helm chart. The charts are way more complicated for a WordPress application with so many files and very complex templating. And we will look more into templating and get into the details about these charts later in this course. But for now, we will stick with simple charts to understand the basics. Now, when a chart is applied to your cluster, a release is created. Now, we could ask ourselves, why the need for an additional item? Why can't we just say we installed a chart to Kubernetes? Now, in the command helm install my site, Bitnami WordPress, we used the chart at Bitnami WordPress and named the release my site. So why not just use a shorter command like helm install Bitnami WordPress and be done with it without specifying a release name? Well, one simple reason why it makes more sense to have releases based on charts is that we can install multiple releases based on the same chart. So we can launch a second WordPress website with a command such as helm install my second site, Bitnami WordPress. And since there are two different releases, they can be tracked separately and changed independently. Even though they're based on the same chart as releases, they're two entirely different entities. Now, this can be useful in a lot of scenarios. For example, you could have a release for a WordPress website that your customers use, and another release for a WordPress website that is only visible to your internal team of developers. There, they can experiment and add new features without breaking the main website. And since the two releases are based on the same chart, once they get something working correctly on the development side, they can transfer it to the main website since it should work exactly the same way, as the two websites are basically clones and built the same way. Now, we saw an example of a very basic chart developed in Helm. And earlier, we saw an example of a chart to deploy a WordPress application. And what if we want to deploy a new chart, say, for deploying Redis or Prometheus, for instance? Thousands of charts are readily available at different Helm repositories across the world. There are different providers who are hosting Helm repositories, such as AppsCode, Community Operators, TrueCharts, Bitnami, etc. And you don't have to go to each of these repositories to search for charts. All of these repositories have listed their charts in a single location known as the Helm Hub or Artifact Hub, as it is also known now. So at artifacthub.io, you'll find charts that you can use right away. As of this recording, there are over 6,300 packages available there. And you may search for the chart you're looking for or browse through available ones. And sometimes the charts are actually published by the actual developers of that project. So you will see the official or verified publisher badges in such cases. And it's preferable you use those when available. We'll see more about installing charts from repositories in the upcoming videos and labs. Well, that's all for now. I'll see you in the next one. Let's talk a bit more about Helm charts. Helm is rather an easy-to-use command line tool. You just tell it to install this, uninstall that, upgrade something, roll back to a previous state, and so on, and it proceeds to do all the heavy lifting behind the scenes. It's basically an automation tool where we, the human operators, specify our desired end result, the destination, and then it doesn't matter if 5, 10, 20, or 50 actions are necessary to achieve that end result, to get to that destination. Helm will go through all the required steps without bothering us with the details. But since in the command line, we don't give this tool a lot of info except, hey, I want this installed, how does it know how to achieve this goal? Helm knows how to do its job with the help of what are called charts. Charts are like an instruction manual for it. By reading and interpreting their contents, it then knows exactly what it has to do to fulfill a user's request. As far as the human operators are concerned, charts are just a bunch of text files. Each specific file named in a specific way has a well-defined purpose. For example, as discussed before, in the values.yaml file, we'll find parameters that we can pass to the chart so that everything gets installed with the configuration options set as we desire. Now, we saw this simple example earlier. In this case, we have two objects, a deployment and a service. And it's a standard deployment that deploys pods of an image and a service that exposes it as a node port service. However, you might notice the image name and replicas are specified in a different form. This is called templating. The values that go here are part of the values.yaml file. And we will look into templating itself in more detail later in this course and how to form these values. So the two files are templates. These are customized using the values from the values.yaml file to create the final version of files required to deploy the application on the Kubernetes cluster. Apart from the values.yaml file, every chart also has a chart.yaml file. It contains information about the chart itself, such as the chart API version,